Hello and welcome to Lecture 8. This lecture is about bit operations. In this lecture, we are going to talk about shift operations for signed and unsigned numbers, and also we are going to explain the application of logical operations such as AND, OR, and XOR in assembly programming. Let's start the lecture with logical shift. So the first command in logical shift, that is for unsigned number, is SHL. SHL stands for shift left. So the syntax has two arguments. So the first one is the register or memory, and the second one is register CL, or could be an immediate value, numerical value. So basically you shift the content of the register or memory as much as this immediate value or as much as the value that is stored in register CL. So shift left start by shifting the most significant bit to the left. So it's basically the most significant bit gonna be stored in carry flag. So we will illustrate how this shift left operation is done on a register or memory in the next few slides. So the next operation is shift right. So the acronym for that is SHR. It also has two operands. So the first one is the register, a register or a memory, and the second one is a numerical value or register CL. So shift right is going to, when you apply shift right, is going to impact the least significant bit, where the least significant bit is going to move into the carry flag, and the rest of the bits are also going to move to the right as much as the value that is stored in register CL or specified by immediate number. Let's take a look at some example. Assume that in here we have this hex number stored in register AX. When we use this command, shift L AX 1, meaning that whatever value that's stored in register AX, then it should be shifted as much as 1 bit. So what you do to see that impact is that you just take the value of each hex digit and convert it to binary value. For example, C is 12, therefore it's going to convert to this. And then you have 4, and then you have 7, and you have A, which is the value of 10, where it can be written as the combination of 8 and 2. So in binary, it's going to be 1, 0, 1, 0. So when you say shift left, meaning that each bit from this side is going to shift by 1 bit to the left. Therefore, 1 is going to go to the carry flag, and the rest of this bit gonna be going shift as much as 1 bit. So this bit is going to be here, 1, 0, 1, 0. This kind shifted here, is here, and then we have the rest of the bits shifted as much as 1 bit. So the boundary changes in here. Therefore, here as well. Okay. Then we have 1001, and then we have 1, 0, 0, and the bits that coming into the register is going to be bit number 0. So this is the result of the shift for this value. So the second one is shift right AX as much as 3. So you have your register AX, now you shift it to the right for 3 bits. The process is the same. We are going to see more detailed example in the next few slides. In this example, we move number 10 into register CL, and then we do the shift left on register EAX as much as the value that's stored in CL, in which for this case is 10. We basically shift register AX as much as 10 bit to the left. All right, here we have some numerical value for clarification. So we have SHL shift left and SHR shift right. So for this one, we have this number, put it in register AL in here, represented in with this bit, and then we use shift AL, and we want to shift it as much as 1 bit. So as you can see from here, so 1 is going to go to the carry flag. So it's going to be here. And then the rest of the bit gonna shift it as much as 1 bit. So here is what happened when you shift it. And then when this space gets empty, the value that entered to the first bit is going to be 0. So the next sample is this one. You do shift right AL as much as 1 bit. In this case, then 1 is going to go to the carry flag. And then the other bits are going to shift it as much as 1 bit. So here is what happened. And the first bit, when it gets empty, you just fill it out with value 0. Okay, let's see a simple program with an application with shift left operation. Alrighty, in here we have a simple program. In here, define message and set, okay, shift must be less than or equal to 32 bits. This is a message that's going to be printed out as error message. What we want to do, we just want to read a number from the screen and start shifting that number as much as the second number that we read from the screen. And then we want to check if the second number, the value is more than 32 bit, we're gonna just throw an error message on the screen saying that, okay, the value is greater than 32 bits, so this program will not work. So it asks the user to enter another value which is less than 32. Okay, so let's go to the program. So we read one integer. It's going to be stored in register AX. We move it to EBX, and then we have the second read. This time we read it. This is going to be stored in register EAX. In here, we compare EAX with 32. We say that if the second number is greater than 32, that's an error. Go to the error message in here and put this message, where this message is this one, saying that the shift must be less than 32 bit. So if AAX or second number is not going to be greater than 32, then we continue the program in here. So in here, we move the value of AL into register CL, and then we shift left the first number as much as the value that's stored in CL. Finally, we move the value into register EAX to be printed out with this command, and then we print out the new line command after that, and finally we jump to the end of the program. So this is what this program does. It takes two numbers and shifts the first number as much as the second number. The program also checks if the second number is greater than 32-bit, it throws an error message on the screen and exit. This one is an example with shift right. Again, we read two numbers. We store the first one in EBX. We read the second number, store it in EAX. We here again do the same process. If the second number is greater than 32, we throw an error message on the screen. If not, then we move that value to register CL, and then we shift right that, and then finally we print out that the shifted number on the screen, and we end the program. So these programs are uploaded into Canvas, so you can go and download those programs from Canvas and run it on your machine to see the result. Okay, so there is an application for shift operation to calculate the power of 2 or to divide a given number by a value that is power of 2. So let's see how this works. So shift left EAX3. Basically, this operation takes the value of EAX, multiply that value by 2 to the power 3, and store the result in EAX. So let's see an example. Assume that the value that is stored in register EAX is, for example, number 2, and so this is a 32-bit register, is EAX, and we simply shift left this as much as 3 bits. Let's see what's going to happen. So when we shift left this as much as 3 bits, so this 0 is going to be shifted to the left for 3 bits, okay. And then we have our other bits in here. The second 0 also will be shifted as much as 3, and 1 also is going to be shifted as much as 3 bits. Okay, and then so we have 0 in here, 0 here, and then we're gonna have 0, 0, 0. Why? Because we shifted 3 times, so 3 space. We make 3 space, and all those space are filled up with 0 from the right. So now see what this number is. So the number that's stored in register in here is 2. See what this number is. So this number is 2 to the power, this one is to the power 0, this one is to the power 1, to the power 2, to the power 3, and this one is to the power 4. It's basically 2 to the power 4, which is equal to 2 multiplied by 2 to the power 3. Basically, we take whatever value was in the register EAX and we multiply that value by 2 to the amount of the shift left, which is to the power of 3. So this shows that this argument or this mathematical expression is correct. So shift right operation, on the other hand, take the value of its first operand, which in this case is EAX, and divide that value by 2 to the power of the second operand, which in this case is 10. So you can also have an example for this. Simply assume that we have number 4 in here in register AX, number 4, and we want to shift it as much as 1 bit. Let's see to the right. Let's see what's going to happen. When we shift it to the right for 1 bit, this 0 is going to fall out. It's going to go to carry flag. This bit is going to be here. This bit is going to be here. And then 0 and the rest of the bit are 0. So if you take a look at the content of this register, the value is 2. Basically, you divide 4 by 2 the power of amount of the shift to the right, which is 1, which is going to be 2. So this is an illustration of how this shift right operation can divide the value of the first operand by 2 to the power of number of shift rights. So how about sign numbers? If we want to use the shift left operation, what's going to happen if we simply use the shift left operation for sign numbers? If the number is positive and we shift it to the left, okay, we are going to be uh, filling up the number from the right with 0, and whatever value is in here gonna fall out. If our number somehow has a sign bit and the sign bit change as a result of the shift, then we are going to have a problem. Therefore, as long as you use shift left for sign number and the sign bit doesn't change, then the result is going to be correct mathematically. For example, it's going to be multiplied by 2 to the power of number of shift. But when the sign bit changes, the result is going to be different. Okay, this is an example of shift left operation. In here we have -1. We shift it to the right as much as 1 bit. -1 basically multiplied by 2 to the power of 1 become -2. Here the sign bit didn't change, therefore our result makes sense. In here too, if you look at this, the sign bit doesn't change, therefore the result will make sense when you make a shift left. So the conclusion is that as long as the number stay negative for negative number and for positive number, if they stay positive, then the shift left operation can be used to multiply that number by 2 to the power of number of shift left value. The conclusions. Okay, how about shift right operation? Shift right operation is a bit different because when you do the shift right, you basically fill up the most significant bit with 0 value. So this is your register and this is your sign bit. So when you start doing the shift right, the first thing you do, you fill up this most significant bit, which is your sign bit with value 0. So if the number is negative, then you put 0 in here and you change the sign and number become positive. Therefore, we are going to have problem right away. So using shift right, SHR for sign number does not make sense mathematically. So in here we have an example, a negative number. We start shifting that to the right as much as 1 bit, and we'll get this one where the number is positive. So you see that -4 converted to 126. So the result is not going to be actually divided by 2 to the power of number of shift. Let's see what the solution would be for this case. Okay. In this case, if the number, when we doing the shift right operation, right? If the number is going to be filled out with 1, then our result is going to make sense. So take this number and then shift it to the right, but you fill out the sign bit with its own value. Therefore, -4 is going to be divided by 2 to the number of shift, which in this case is 1, and therefore the result is going to be -2. Therefore, when you do the shift right, if you fill the most significant bit, when you do the shift right, you have to fill up the most significant bit with the sign value, whatever it is. If it is 0, put 0 in there. If it is 1, put 1 in there. See if we have a solution in assembly programming for this situation. So this is the conclusion that we talked about. The solution for this is to use arithmetic shift instead of logical shift. Arithmetic shift is used for sign number. So when you want to apply shift to a sign number, you use SAL, stand for shift arithmetic left, or SAR, shift arithmetic right. So for SAL, nothing going to be different from SHL. So basically, these two are going to be alias, meaning that SAL is similar to SHL, but SAR is different than the logical shift right, in the sense that when we want to shift to the right, instead of like putting 0 in the sign bit, we replace that sign bit, that shift with the previous sign bit. For example, for this case it was 1, therefore we put value of 1 in here, and we shift the rest of the bit as much as 1 bit. That's the only difference. So the first example that we have in here is that we move number 10 into register AX, and then we use shift arithmetic right as much as one bit. Since this is a positive number, therefore SAR is going to be similar to SHR, so they're going to be similar. Then here we have number 10, we're going to shift it to the right as much as 2 bits. Then here we shift the content of EAX as much as 20 bits. In this case, we have -1 stored in EAX, and then we use shift arithmetic right to shift it as much as 1 bit to the right. And here's a code that shows the application of shift arithmetic right. Basically, this code only is for demonstration to show you how you could use the SAR to shift the sign numbers to the right. This program is similar to the previous program. You read two numbers, then you compare the numbers, the second number with 32. If it's greater than 32, just throw an error message on the screen. If not, you go in here, you take that value, put it in SAL, and in this case, you use shift arithmetic right. Therefore, your number in here, your first number could be a negative number. That's the only difference with the previous program that we had in this lecture slide before. Here we have a practice example. So we basically read an integer from the standard input. Then we initialize EBX with value 0, and then we initialize register ECX with value of 32. And then we start shifting EAX as much as 1 bit, and then if there is no carry, then we go to L1. In L1, we say loop, start loop. Basically, when we do this, we are going to reduce the value of the register ECX by 1 and going to this loop. So if there's carry, then we increment register EBX. And if there's no carry, we are going to shift the value. So what it tells you is that, so you have your register in here, you have some value stored in here, you start shifting those value to the left, and then you know that the first bit that comes out is going to be in the carry flag. So you check the carry flag. If your carry flag is 1, then you increment your EBX register, which is initialized with 0. So for every 1 that you get into the carry flag, you increment your EBX register. Therefore, this program computes the number of 1 that is exists in your first number. So it counts the number of 1. So that's an application of the shift left operation. Okay, this is the second form of count bits program. Basically, in this program, what you see in here is roll, and what you see in here is shift left operation. So what it does, it's actually the same. So you have again your register, then you have your carry flag, but one thing is going to change. So in normal shift left, whatever value you have in here, then it's going to fall off, and then you don't have access to it. But ROL is going to rotate that number back into your register. Therefore, if you shift 32-bit register as much as 32, then after you complete the 32-bit shift, your register is going to have the same value as it was at the beginning. Therefore, EAX in this operation, its value will not change. But he again counts the number of bits by checking the carry flag. Okay, so there is a third form of count bits program. In this form, we again going to use the roll operation, which is going to rotate left the content of EAX operation. But instead of checking the value of the carry flag, we are going to use ADC operation. Basically, we have our register EBX that count the number of 1 for us. And what we do, ADC is basically add its operand, its 2 operand, which in this case is EBX register and 0 with the carry flag. Therefore, your EBX value is going to be equal EBX plus the carry flag. That's the reason if you have your register in here and then you shift left and the value going to the value that is going to the carry flag, so whenever it is 1, it's going to be added to our counter, and therefore whenever it's 1, EBX is going to be incremented. But whenever it's the bit is 0, so when you add EBX with the carry flag, it's gonna stay the same. Therefore, it's only increment when the carry flag bit is 1. So as you can see from here, this program is shortened as much as 1 line, which reduces its complexity. So we basically get rid of these 2 commands and replace those 2 commands with ADC. Okay, rotate instruction we used in the previous program also has its own form. So we have rotate left, rotate right, rotate with carry flag, and rotate with carry flag to the right. So these are the different forms. So if you have your register here, and then you have your carry flag here, when you use rotate left, so these are your bits, the carry flag going to have the value of the most significant bit in each rotation, but the way that we rotate is this way. But when you have rotate carry flag left, you have the carry flag in loop. So you have your carry flag. Therefore, this is the way that rotation happens for this command. And for rotate right, then again, you have your carry flag in here. So the direction that we are rotating is this one. So always the less significant bit going to be copied in carry flag, but we are going to rotate the value of the register like this. So rotate, RCR is rotate with carry flag to the right. It means that you have your register in here, you have your carry flag in here, then your carry flag will also be going to be in the loop of the rotation. So therefore this one, implementation is illustrated with this figure. So in the previous example, we had basically rotate left, where the rotation happened in this way. Okay, the next topic is bitwise operation, and for this our focus is on AND or XOR and NOT operation. We have seen these commands before, but in this lecture we are going to see some of the application of these logical operations in assembly programming. So as you know, when you have AND source and destination, you basically do the source, do the AND with the source. Let's say, just say AND with the destination, and then put the result back into the source. Same thing for OR, same thing for OR, XOR, and NOT. Okay, here there are some examples. Or EAX with 100 binary. You basically, whatever value is in EAX register, you're going to be ORing that with EAX register and put the result into EAX register. In here we have AND operation, XOR, OR, and XOR. So basically for the first one, you have your EAX register. It has some values in it, for example, 1, 0, 0, 1, and the rest is 0. And then you want to be ORing that with 1, 0, 0, 0, and the rest is 0. So what you get at the end is the bitwise operation, meaning you do the OR operation for each corresponding bit. Therefore, you're going to have 1 in here, 0 here, 1 in here. And if this one is 1, then we're going to have 1 in here. And the rest of the bit is going to be 0. So this is what we mean by bitwise operation. We do the operation by bit. You can do the same for AND. You just convert this hex number to binary, and then you have your BX register, whatever value is in your BX register. Then you convert that hex number and put it in here. For example, this one is F. You're gonna do 1111, and then this one is D. You are also going to do that to convert that and put it in here. So D is D EF. Therefore, the value is going to be 1. So it's going to be 8 plus if we say 4, and then we are going to be having 1 and then 0 in here. And the rest of the bit 111, 111 in here. And then your register BX, assume that it has a value of 0000. Then here 111, then here 000, and here assume 000. So once you do the AND between these two, you do the bitwise AND. Therefore, 1 by 0 gonna be 0. So the first 4 gonna be 0. And here we have 1 AND with these guys. So this one is gonna be 1, 0, 1, 1, and the rest is going to be simply 0. So this is what the value is, and it's going to move to register BX. I know all of you are familiar with this topic, so don't spend much time to do the rest of this operation. So we move to the next topic. So here is a practice example. This example is available in the program. You have this number, you're gonna AND it with this, and then you print the result and this on the screen. So, but the number that is in EAX register comes from the standard input using this syntax. Okay, so we can use these logical operations to change the nth bit of a register. So let's take a look at some example in here. So assume that we read two numbers from the input A and N, and we want to change the nth bit of the first number. So how we can do that? First, assume that we want to set that nth bit. When we say set, means that we want to turn on that bit or change the value of that bit to 1. Or when we could just unset that bit, meaning that we want to turn off that bit, or clear that bit, or set that bit to 0. Or we want to flip the value of that bit. Flip, the surname could be switch, or we want to do the complement, or we want to invert that given bit value. Okay, let's do this. So we read the number from the input, we move it into EBX register, and we read the second number, and the question is how we want to set, unset, and flip the value of the EBX, actually the nth bit of EBX, to be set, unset, or flip. Let's see the code. So I suggest you, before taking a look at the code to do the set, you try it by your own, and then you play the video after your pause. Okay, we would read the number, we put it in EBX, we read the second number, we put it in the CL, and then we basically initialize register EAX, and then we shift that 1, which is in EAX, as much as CL number. Then we OR our first number with the value of EAX. Let's see one example for setting nth bit of a number, and then move on to the next bit manipulation operation. Assume that the first bit that we got is 5, 1, 0, 1, 0. Our first number that we read from input is value 5, and we put this value in EBX register by this command. And then we read the second number, and the second number, the value is 2, is going to be stored in register AX, therefore it's going to be available in register AL, and then we put that AL into CL, therefore the value of CL is going to be 2. Okay, then we move the value of 1 into AX register. So AX is going to have value of 1. And then we say shift left AX as much as CL. So when we say shift A, AX as much as CL, we shift basically CL as much as value 2. Therefore, we shift once, it's going to go in here, and we shift the second time, then 1 is going to be here. So therefore, these are going to be 1. Therefore, this is our nth or second bit of the register AX, which the value is 1. Note that the first bit is bit number 0, second bit is bit number 1, and third bit is bit number 2. So in this example, we want to set bit number 2 of the input, which in case is EBX. Therefore, we want to set this one. Let's see how program can do this. So we shift left EAX as much as that. So we obtain this. And then finally, we OR the value of EBX with EAX register. So this one is EAX and this one is EBX. So we basically going to OR 1, 0, 1, 0 with the value of 0, 1, 0, 0, which is this one. So the first one is this one. So when we do the OR, then we get 0, 0, 0, 0, 1 is going to be 1, and 1, 0 is going to be 1, and finally 0, 1 is going to 1. Therefore, if you take a look at this, it looks like that we set the second bit of the input, which is this one. It was 0, and now it's set to 1. So this is how we set nth bit of an input using shift left operation and logical OR. So how can we unset nth bit of an input A? So you do all those things the same, but this time, once you get your value of EAX, you note that value, and then you use AND to make that given bit 0. Just give an example for yourself. Again, you can assume that your EBX has value of 9 and your EAX has value of 3. Just follow this process, convert this 9 into binary value, and convert this 3 again into a binary value, and see after this operation what's going to be the value of EBX. So the thing that you're going to be getting in here is going to be the bit third, which is this bit. You are going to be unset this bit, and basically this is going to be converted to this number. Now I'm going to be converted to 1. This is your 9, the input. When you unset the third bit, is going to convert to 1. Okay, the flip is another thing. For that, you use XOR operation. Just follow one of the example above and apply this XOR to see how the flipping is going to happen. And then this example shows you how to check the nth bit of an input. So basically read one integer, and then you will end it with bit number 7. So in here we want to check whether bit 7 is on or off. That's the reason we make AX this value. This is the bit 7 of it. Therefore, if the value after AND, if you do this AND, if the value of the 7 bit is going to be 0, then this jump is not going to happen. And if it is actually 1, so it's not going to happen. Therefore, you're going to go to on label and print out that, okay, bit 7 is on. But if this bit, the bit 7 is 0, then the result of this AND operation is going to be 0, and therefore you're going to go and move this message into EAX, and you're going to jump into NL, which is in here, and print out the string, call a string, which is going to be the second message saying that bit 7 is off. Okay, in this example, when we check the value of the nth bit using this program, as you can see from here, after doing the AND, the first 7 bits of the AX register is going to convert to 0. Therefore, if you want to keep the value of AX register as the same as before, what you need to do is two things. You need to store the value of AX, copy it into another register, and then examine that with this value. So we want to see if there is any other assembly command that we can use to check the nth bit, but the content of the AX register doesn't change. The command is test, basically. So basically, you can use test command to check if the nth bit is 0 or 1, and still your AX register, the content won't change. So let's see how this works. Basically, test works similar to AND operation. It changed the flags, the flags in the flag register, but it doesn't keep the value of the AND operation. It just does the AND, but it doesn't move the resulting value into AX register. So AX register, the content going to be as the same as before, but after this test operation, the flag registers, all the flag bits going to be impacted, and therefore you can use J not 0 flag to test to see what happened to the value of that and then make a decision from there. So in summary, test is similar to AND operation. It changed the flag registers similar to AND, but it doesn't change the content of the first operand, which in this case is AX. Okay, we have some practice over here using XOR operation and the application of it. So basically, when you use XOR operation 3 times in a row, you basically change the content of the two operands, in this case, EAX and EBX. Okay, parity flag, as you remember from the previous lecture, parity flag checks if the number of bits in the first byte of your result is even, then it's going to be set to 1. If the number of ones in the first byte are odd, then the parity flag is going to be 0. So appendix of the textbook shows a lot of this instruction and how the flags bits are impacted. So take a look at the textbook to find out more details about these logical operations. This is the end of lecture 8. See you on the next video.